Welcome friends, welcome to Basic Electric Circuit course. We are here in the module number 6 and in today's class we will be discussing mainly on second order circuits. So let us begin our class. So in the second order circuit we will be looking mainly on series and parallel circuits, that is R, L and C, the three components, basic components of any device, that is a resistor, inductor and a capacitor. So we can either join them in series or in parallel or some kind of a mixed connection, but in today's class we will be mainly focusing on series and parallel combination of RLC circuits. So let us start our class for today. So let us first of all have some brief look for the RLC series circuit. So in case of RLC series circuit, when connected across excited by a DC supply and without a DC supply. So let us draw a RLC circuit. So we have a resistor connected in series with an inductor and finally a capacitor, and if we excite this by a DC source of voltage Vs and the respective components are resistance of R, inductance L and capacitance C. So in this case current will be drawn by the RLC combination, and we first of all need to determine what will be the nature of this I function IT. So the objective is simpler. We will just start writing with the KVL, that is the Kirchhoff's voltage law. So writing the KVL. So in case of RLC series circuit, we'll write the voltage drop across each component, and the total voltage drop should be equal to the voltage of the supply. So Vs should be equal to the current I, which is the function of time, multiplied by R, that is the potential drop across the resistor. Then we have potential drop across the inductor, that is L into di by dt, and plus in case of capacitor, this is the integral form, so 1 upon C IT dt. So this is a simpler relation that we can get from the KVL. But we also know that suppose across the capacitor, if the voltage drop is V, small v, so in that case we can also write that the current will be C into the differential of dV by dt. So now we can replace the term I here in the above equation by equation 2. So substituting this in 1, so let this be 1. So substituting this in 1, we can write Vs is equal to, so C into dV by dt, dV by dt times R plus L. Now in the inside the differential we have d by dt, and now substituting C dV dt, and we can simply write the third term as small v, that is the voltage drop across the capacitor. So now as you look, this relation becomes Vs is equal to C times R dV by dt plus LC into d square V by dt square plus V. So since this is a second order term here, second order differential, that is why we are calling this circuit as a second order circuit. So these are second order circuit, and in the previous class we have looked for RC and R and LR circuits. Those were first order circuits because only first order differential was formed. So I will not go into the solution for the second derivative equation. I will just write it down, the solutions for the RLC combination. So we can do this by solving a problem here. So let us say that there is a given circuit, and for the circuit in figure, we have to find the voltage drop across the capacitor, so as a function of time, and also we have to find the current, so the current passing through the inductor. And it is given that for t greater than 0 we have to find these values. The resistance R here is 5 ohms. So first of all we have to look for the initial conditions. So let us see what are the initial conditions, that is at t 0 minus, that is before the switch has been opened. So before the switch has been opened, the circuit here will look like, so there will be a voltage source, a resistor R, an inductor, then the circuit switch is closed here, and we have a 1 ohm resistor and a capacitor. So since the circuit has been in this position for long time, so therefore inductor will behave as a short, that is there will be no potential drop across the inductor, and the capacitor will be a open. So the capacitor will behave as a open circuit. So to simplify the circuit, we can remove this inductor just by a resistor, and we can also delete the capacitor portion. So the circuit simply looks like this when the switch is closed. So now we have to first of all determine what will be the voltage across the capacitor. So this is the point where the capacitor is connected, which is currently open circuit. So the potential drop across the capacitor will be same as the potential drop across the 1 ohm resistor. So using the voltage division rule, so the voltage drop across the capacitor V at time equals to 0, that is the initial condition, will be 24, and 1 ohm across 1 ohm resistor we are trying to calculate, divided by the sum, that is 5 ohm plus 1 ohm. So this will become 24 by 6, that is 4 volts. Okay, and also we need to find the current I at initial time, that is 0 seconds. So I at 0 seconds, we have to also determine the value of I. So the value of I will be the total current drawn by the two resistors, that is 5 ohm and 1 ohm. So that will be 24 divided by the sum of the equivalent resistor in series. So this will be V upon 5 plus 1, that is 24 by 6, that is 4 ampere. So a 4 ampere of current is being drawn. So these two are our initial conditions. So that is at t 0 minus we have found the initial conditions. Now there is a shift happening here. We are opening the circuit at time t equals to 0. So for the case when time t is greater than 0, we will draw the circuit. So I will remove this circuit which was for time t equals to 0 minus, and I will redraw the circuit for time t greater than 0. So now the switch is opened. So this is a voltage source, there is a resistor 5 ohms, there is again an inductor, and since the circuit is opened, so there will be no current will move in that portion. And now we have a capacitor 0.5 farads and an inductor 1 Henry. So now this is a RLC circuit, as all the three components, resistor, inductor and capacitor, are present in this circuit. So now we have to solve for this. So first of all we need to understand what will be the equation for the second order differential equations solution. So first of all we need to find out which case is it. Is it a, so there are three cases as you have already learnt in the class. So the cases can be underdamped, critically damped, and overdamped. So first of all, we have to find out. So can anyone tell me what are the conditions? So suppose for underdamped, what will be the condition? Then that we can say that the circuit is currently underdamped. And what will be the condition similarly for all the three cases? So anyone, if you have already gone through this topic, please tell. So I will give options. So suppose there are two terms, alpha and omega. So these are the characteristic roots, alpha and omega. So when alpha is less than omega naught, in that case, what will be the case? A, B or C? Please write your answer. What will be the case when alpha is less than omega naught? Yeah, very good. So Kyle has answered. This is the case for underdamped. Okay, and similarly for critically damped, the case is alpha is equal to omega naught, and in case of overdamped, we have alpha greater than omega naught. So these are the three cases here. So before moving to that, first of all, we need to find what is the case for our circuit. So what will be the alpha and omega naught value? First of all, we have to calculate alpha and omega naught for our circuit. So let us do that. So in case of series RLC circuit, alpha is given by R upon 2L. So the resistance was given 5 ohm and the inductance was given 1 Henry. So it will be 5 upon 2 into 1, that is 2.5. So I am not writing the units here because it will unnecessarily make the problem complex. So alpha is 2.5. Now we have to find the oscillating frequency omega naught, that is given by 1 upon root LC. So what will be 1 upon root LC? So L is 1 Henry and C is given as 0.5 farads. So we'll put 0.5. So what will this value come out to be? So use your calculator and find the value. 1 upon root LC. So 1 divided by square root 0.5. This comes approx 1.4. So Kyle, you are getting value 2. So how you are getting 2? So L and C are given here in the problem. L is given 1 Henry and C is given 0.5. So 1 by 0.5, that we'll get 1.4. So now as you can see, 1.4 is less, that is omega is less than alpha. So we are in the third case, that is overdamped. Our circuit is overdamped. Okay, so now we know the circuit is overdamped. So let me clear this portion. Our circuit is overdamped and we have calculated the values for alpha. So alpha is 2.5 and omega naught is 1.4 and our circuit is overdamped. Okay, so now with this information we can move to the next phase of our problem, that is writing the solution for that differential equation. So in case of overdamped, we can write the voltage across the capacitor Vt as the sum of under steady state condition plus the sum at transient. So steady state is also called the forced condition. That is when we have connected the supply, and transient is free. That is, there is no excitation in the circuit. So let us first of all write the equation in case of transient form. So in case of the transient, we'll write the equations for case of overdamped. So the sum here Vt will be V steady, also called Vf, we are denoting because it is a forced wave, and plus the overdamped condition. So the solution for overdamped is given by A1 E minus T plus A2 E minus. So there we have two conditions, C1 and C2. These are the coefficients. So A1 E C1T plus A2 E to the power C2T. So I hope this is the condition. That is C1 and C2 here are defined by these are the roots C1 and C2. So these are given by C1 and C2 is equal to minus alpha plus minus square root of alpha square minus omega naught square. So now we have to calculate the value for C1 and C2 to substitute here in the voltage equation. So let us call this equation 3. So let us find out. We have calculated alpha, that is 2.5 plus minus alpha square, that is 2.5 square minus omega naught square, that is 1.4 square. So in case of so first of all let's calculate the square root. 2.5 squared minus 1.4 square, this comes out to be 2, only 2, not square root, and minus 2.5. So the respective values will be, so let us say first of all for positive case, 2 minus 2.5, that is minus 0.5. So let us say C1 as minus 0.5 and C2 as minus 4.5. So now we have the values C1 and C2. So let us substitute C1 and C2 in equation number 3. So then in that case we'll having V of t is equal to Vf plus A1 e to the power minus 0.5t plus A2 e to the power minus 4.5t. So this is the equation, but still we have two coefficients A1 and A2. So we need to find out what will be the A1 and A2 values and what will be the Vf, that is the forced voltage. So I will just keep the equation part here and remove all other portion. So the equation part is, this portion is our major equation for which we need to find out the value of A1 and A2. So this is minus 4.5t. Okay, so let us first of all find Vf. So what is Vf? So again we will look into the circuit. So Vf is the final voltage across the inductor, across the capacitor, this voltage V. So suppose for the final circuit, if we have left the circuit in this position for a long time, in that case the inductor will become a short circuit. So I will just draw the circuit for t very greater than 0, that is at some long time. We will have a voltage source 24 volt, a resistor will always be there, it is not a function of time, but the inductor will become a short now and the capacitor will become open. So the voltage drop across this will be, since there will be no current drawn, so the same voltage, that is the voltage of source, will be the Vf. So Vf will become 24 volts. So let us put Vf. Vf is 24 volts. Now plus A1 e to the power minus 0.5t plus A2 e to the power minus 4.5t. Okay, now we have to take the two conditions. So suppose first of all you have to find the voltage at 0 time. We have to that those initial conditions that we have already found. So we have already calculated the initial conditions. So these are the initial conditions. Initial conditions. So we already know V at 0. So let us substitute V at 0. So V at 0 will become 24 plus A1 e to the power 0 will be 1. So that portion is gone, and again e to the power 0 is 1. So it is A1 plus A2, and we already know V0. So V0 is 4 volts. So let us substitute that. 4 is equal to 24 plus A1 plus A2. So therefore the first part we will be getting, so I'm just writing the parts here. A1 plus A2 will be minus 20. Okay, so this portion is now done. Now we have to, what other initial conditions we know? We know I0, that is the current through the inductor, we know. So let us take that value also. So we can write the we already know the current through the capacitor is given by I is equal to D into the voltage drop at the capacitor, differential of voltage drop across the capacitor by time. That is the differential of voltage with respect to time. So at I0 this will become I0, this is C, since C is a constant term, V0 by dt. So now we already know the function V of t. So we have to now differentiate once. So I0 will become, so how much was the capacitance? C was given 0.5. So 0.5. Oh, and the I0 was also given. So let us substitute I0 also. So I0 was 4 amperes. So again I am putting 4 amperes in the LHS portion. Now we have to differentiate our equation, our differential equation. So let us differentiate it. So 0.5 multiplied by the differentiation of 24 will be 0. So we are not taking that term. Now let us differentiate this second term here. So the second term here will be written as, so I'll write here minus 0.5 A1 e to the power minus 0.5 t, okay, plus again minus, since the exponential power is minus 4.5 A2 e to the power minus 4.5 t, okay, and since t is 0, since we have found this current at time 0, so this here sending this term in the LHS portion, so this will become 8 is equal to minus 0.5 A1 and minus 4.5 A2. So let us write this part also here on the right side, that is minus 0.5 A1 and minus 4.5 A2 is equal to 8. Okay, so let us multiply it by 2. So if we multiply this by 2 in the LHS and the RHS, it will become minus A1 minus 9A2 is equal to 16. And we already have the first equation part here, that is A1 plus A2 is equal to minus 20. So adding these two parts, A1 and A1 will get cancelled. It will be minus 8A2 and this will be becoming minus 4. So A2 will become 1 by 2. Okay, A2 is 1 by 2. So similarly, what will be A1? So A1 is minus 20 minus A2, that is minus 1 by 2. So this will be minus 41 by 2. Okay, so till this point I think everything is clear. We have found the values for A1 and A2. This is A1 and this is A2. So let us rub the portion. We have already calculated these values. So I will just now substitute A1 and A2 in our original equation of Vt. So V of t will become 24 plus A1. A1 is negative, so it will be minus 41 by 2 e to the power minus 0.5 t. Okay, and A2 is 1 by 2, positive 1 by 2, so 1 by 2 and e to the power minus 4.5 t. So this is the voltage waveform. So I hope up to this point it is clear. So one thing we can do is that we can plot this function and see how this looks. So we'll just plot this function and try to see how this function looks. It will be look for us. So let us do that plotting here. So I will just change my screen into the full mode, that is, let us see the how this function will look when we plot this function. So let us open MATLAB. So I hope you are familiar with MATLAB. So let us open MATLAB and we'll try to plot this function and how this function looks in MATLAB. So let us do this. So MATLAB will take some time to open. Okay, so we are now in MATLAB. So let us create a new script here. Okay, so let us write the header files here. So the header files are quite common, so I will just copy and paste it from some earlier codes. So we will clear the variables, we will close the windows that are there already, that is close all and CLC to clear the command line. Okay, now let us define time. So we'll be plotting time. Let us say time equal to t, and time, let us distribute our time from 0 second to 100 second, and let us have 100 points. So this is our time. Okay, now we have to write the function for our voltage. So let us say our voltage is equal to V. So V is equal to, we have already calculated the function V, that is 24 minus, it was 41 divided by 2. So 41 divided by 2 and then multiplied by, so multiplied by exponential exp, and the function was minus 0.5 times time, so multiplied by time t. Okay, and the second term was plus 1 by 2, that is 0.5 multiplied by exponential to the power minus 4.5 times time. So this was our voltage V. So let us plot this. So for plot we have to plot against time, so t comma V. So P comma V. So let us save the code. So this is RLC circuit, so let us name it RLC. circuit. I will just save this at my desktop. Okay, so let us plot this, run the code. So this is how our plot looks like. So at time equals to 0, the current was the voltage was 4 volts. Okay, so we had already seen the voltage here. Initially, we had calculated voltage V as time equals to 0 as 4 volts. So this is the 4 volt. At time t equals to 0, we are getting 4 volt. So our wave function, this means, is correct. That is, we are getting 4 volt at time equals to 0, and as the time moves, this just return back, so the voltage starts to catch up, the voltage is increasing, and finally at this point, around x, that is our time, around 12 seconds, 12.12 second, the voltage has reached 23.9 volts, and finally at some more time the voltage has slowly moving towards 24 volts, and finally at some long time, suppose 50 seconds, the voltage has reached 24 volts. So again, as you can see, our forced voltage Vf was 24 volts. So our forced voltage was 24 volts. So the circuit has, on the long term, will reach the steady state condition at 24 volts. So we are perfectly fine with this equation. We have already tested this equation on plotted it using MATLAB, and finally calculated the curve. So now let us move on. So let us move on to our second case, that is the RLC parallel circuit. So I will just change my screen to the notepad. Okay, so we are now moving to RLC in parallel. So let us draw a circuit, a simple RLC circuit. We'll be having, so as per nomenclature, first is resistor, then is inductor, and finally there is a capacitor. And across this we'll have a source, current source, let us say a constant current I. So R, L and C. So again, the process will be simpler. We will first of all find the initial conditions, that is at t equals to 0 minus, what will be the conditions, that is these conditions are called initial conditions. And the second case is at t greater than 0, we'll find the waveform. But in this case, we'll find the equation for current I, that how much current I will be drawn by the inductor. And similarly, you can also find the voltage across the capacitor. That is, what will be the voltage across the capacitor. So again, I will not go into the derivation for the equation for the second order differential equation. We'll just try to understand this problem by solving a question. So let us attempt this question. So in this question, a circuit is being given. So in the question it says, in the circuit in the given figure, find I of t, that is the current through the inductor. So this is I. So this current we have to find. So let us first of all write the initial conditions. So initially when the circuit was, the switch was open. So in the question they are saying that the circuit is getting closed, the switch is getting closed at t equals to 0. So we'll draw the circuit for t less than 0 or t 0 minus. So at 0 minus we'll be having a 4 ampere source. There will be an inductor and the circuit will be here opened here as the switch is not closed. And finally we have a resistor 20 ohms and a capacitor that is of 8 millifarads and a resistor 20 ohms. So the resistor is here 20 ohm and a source is given plus minus. So the source here is given voltage source Vs as 30 U of minus t. So this is a step signal. So step signal is defined by U of t is equal to 1 for t greater than 0 and U of t is equal to 0 for t less than 0. So since the signal here is a negative sign minus t, so in this case the for a negative value of time, that is U of t will become 1 when t is less than 0, since this is a negative sign multiplied here. And for the time t equals to greater than 0, this will be 0. So t greater than 0 will be 0. So this will be the case in our case. So since the time is negative here, that is before the switch getting closed, so this will be plus 1. So 1 into 30, that is 30 volts. Okay, so this is our initial condition, initial state of the circuit. So let us find out first of all the current I of 0. So since there is no distribution of current, all current will pass through the inductor. So this is 4 ampere. And we have to find the voltage across the capacitor. So the voltage across the capacitor will be same as the voltage drop across the 20 ohm resistor. So these are 20 ohm and 20 ohm, both resistors are same. So the voltage will be divided half for the 20 ohm and half for the other 20 ohm. So voltage across the capacitor will be 30 by 2, that is 15 volts. So these are the initial condition for our circuit. And also you can find the current through the resistor IR. So this will be IR at 0. So the voltage drop is 15. So 15 by 20. This will be the current. So these are our initial conditions. So these are the initial conditions. Now let us see what will happen when the switch is closed. So for that case, we'll draw the circuit again when the switch is getting closed. So this is a 4 ohm current source connected to an inductor. The switch is now closed. We have a 20 ohm resistor, 20 inductor, and there is a 8 millifarad capacitor. And now in this case there is the voltage source is 0, so it will be a short circuit. There is no voltage, so that is 20 ohms. So this is how our circuit looks like. So now if you can see the 20 ohm resistor here, this 20 ohm resistor and this 20 ohm resistor are in parallel. So we can write the equivalent resistance instead of the whole circuit, we can just draw the resistor equivalent resistance. So R equivalent will be 20 ohm parallel with 20 ohm, that is 10 ohms. So 10 ohm will be the resistance. So now this is a classic example of a RLC circuit. This is a L, this is R, and this is C. So, and these are the three components. So again, we'll follow the same method. First of all, we need to find what is the condition of our circuit, whether it is underdamped, critically damped, or overdamped. So let us first of all calculate omega naught and alpha. So omega naught is given by 1 upon root LC. So this will be becoming, so what were the values? L was 20, C was 8 millifarad. So 1 upon square root L was 20 and C was 8 into 10 to the power minus 3. So how much do we get? Omega naught 2.5. Okay, let me just verify it. 20 multiplied by 8 10 to the power minus 3, 2.5. Yeah, very good, that's a correct answer. Omega is 2.5. And what will be the alpha? So alpha is given by 1 by twice RC. So 1 upon 2 into the resistor R, that is 10, and C, that is 8 millifarads minus 3. So this is 6.25. Let me just check. 2 multiplied by 10 by 8 to the power minus 3, that is 6.25. Yeah, correct, 6.25. So 2.5 and 6.25, very good. So let us write omega naught is 2.5 and alpha is 6.25. So what will be the case, whether this is underdamped, overdamped? Clearly alpha is not equal to omega, so it is not critically damped, but here omega is less than alpha. So whenever omega is less than alpha, it is, the case is, overdamped. So the case is overdamped here. So for overdamped case, we'll write the current. So current I of t again will be the sum, that is the forced current I of t plus the transient, that is the natural current I of t. So I f of t, what will be the forced current through the inductor? So here, as you can find, what will be the I of t, that is the forced current through the inductor. Please tell me the value. So the inductor will behave as a short circuit here. So this portion will get shorted. So if this portion gets short circuited, then all the current will be flowing from here. No current will go through the resistor or the capacitor. So IF will be 4 amperes. So IF of t will be 4 amperes. So let us write I of t is equal to 4. Now we have to write for the natural case, we have to write the equation. So that is A1 e to the power C1t plus A2 e to the power C2t. Now again we have to repeat the same process. First of all, we'll find the roots C1 and C2. So C1 and C2 are given by alpha plus minus square root of alpha square minus omega naught square. So just substitute the values. alpha is 6.25 plus minus square root of alpha squared, that is 6.25 squared, minus omega naught 2.5 squared. So please tell me the value for C1, C2, the constants. So let us first of all calculate the square root. So 6.25 square minus 2.5 square, so this is 5.7, so 5.72, 6.25. so let us say C1, let us say the sum, so this plus 6.25, this will be 11.97, and C2, that is the difference, so 6.25 minus 5.72, so this is 0.53. So let us write the values C1 and C2. So I will just write it here in the top. So alpha and omega are known to us, and C1 and C2 are also known. So C1 is known and C2 is already known, C1 and C2. So, and the case is overdamped. Okay, and we have already some form of equation is already there. So substituting C1 and C2 here. So I of t is equal to 4 plus A1 e to the power C1 11.97 t plus A2 e to the power 0.53 t. So we have these values. So we have done some mistake here because the value has to be negative value since the case is here overdamped. So the equation here is minus alpha plus minus alpha square omega, so this will be minus term here. So when this is minus, the equation C1 and C2 will become minus 11.97 and minus 0.53. So now we have to write again. So I of t will become 4 plus A1 e to the power C1, that is minus 11.97 t plus A2 e to the power minus 0.53 t. So this is an equation with two unknowns, A1 and A2. So let us calculate A1 and A2. So these will be calculated from, yeah, it will be minus alpha. So let us calculate this from the initial conditions. So we have already written the initial conditions here. These are the initial conditions. So current is 4 ampere at time 0. So let us put time 0 at t equals to 0. I of 0 will become 4 plus A1 plus A2. Okay, and I0 is given as 4 amperes. So this will be 4 is equal to 4 plus A1 plus A2, 4 getting cancelled. This will become A1 is equal to minus A2. Okay. So A1 is equal to minus A2. This is the first equation. And also from the initial conditions, we know the voltage drop across the capacitor is 15 volts. So let us put that also. So we know voltage drop across inductor will be same as the voltage drop across the resistor, will be same as the voltage drop across the capacitor. So let us write for across the inductor, VL is equal to L into di by dt. since we have the current form IT, that is why we are writing a differential of current. Since we don't know the voltage is equal, but we don't know the exact voltage. What is the exact voltage at each component? It is equal. We know that VL, VR, VC are equal, but we don't know the exact value. So let us put L value is given 20 Henry. So 20, voltage V is given 15 volts. So 15 is equal to di by dt. So again, differential of constant is 0, and this will become minus 11.97 A1 e to the power minus 11.97 t minus 0.53 A2. So write little in the left portion here. So minus A2 e to the power minus 0.53 t. So now again substitute time equals to 0, since the time given here is 0. So this will become so 15. Let us send the 15 in the LHS. So minus 5 is equal to minus 11.97 A1 minus 0.53 A2. E will be e to the power 0 will be 1. So negative can cancel the negative signs here. So 11.97 A1 plus 0.53 A2 is equal to 5. So this is the second equation. So just summarize the equation here. So this equation is, so these are the two equations. Let us substitute equation number 1 into, let us put a value of A1. So 11.97, so 97 times minus A2 and plus 0.53 A2 is equal to 5. So minus 11.97 plus 0.53. This is minus 11.44 A2 is equal to 5. So A2 will be 5 divided by this term, that is minus 4.37. So if A2 97 and 0.53, so I hope I am doing right. So if you found any mistakes, please let me know. So we already calculated the current and the voltage. Voltage was found to be 15. I hope it is correct. So let us write down A1 and A2. So A1 will be minus of A2, that is 0.437, and A2 will be minus of 0.437. So these are the value. So let us once see the calculation here. There should not be any mistake, because if there are some mistake, the final answer and the waveform that we get will be not correct. So we get A1 plus A2 is equal to 0. So A1 is equal to minus A2. Okay, perfectly fine. And in the second part, we found the voltage. So voltage was given by V. Okay. So the voltage term we have written 15. That is, the 15 was the voltage at 0 time across the inductor, across the capacitor, this capacitor, and the same voltage will be at the inductor also, because all the circuits are in series. So V is equal to L into di by dt. So V is equal to L into okay, I will just again check it. V is equal to L into d by dt. So how minus 5 will come? Okay, so let us check it again. So voltage we have calculated it to be 15 volts. So it is 15, and the inductor was 20 henries. So 20 into di by dt. Okay, I think I have done a mistake here only. So di by dt, 4 term will be 0, and this will become minus 11.97 into A1. The exponential part will be gone because we are calculating it at time is equal to 0, and the second term will be minus 0.53. So minus 0.53 A2, and this will be 15 by 20. So I think this is now correct. Yeah, okay, 15 by 20.75. Okay, yeah, I think that is correct. So 0.75 is equal to minus 11.97 A1, and again minus 0.53 A2. Okay, yeah, this is correct. And we know that A2 is equal to minus A1. So 0.75 is equal to minus 11.97 A1, and minus plus, so plus 0.53 A1. Okay, so that is 0.75 divided by minus 11.97 plus 0.53. So this comes out 0.065 minus 0.065 minus 0.065 is the value of A1. So A2 will be positive then 0.065. So this will be the value for A1 and A2. Okay, so let us write value of A1 and A2. So A1 and A2 are now known. So these are A1 and A2. So I will rub the extra portion only up to the equation. So let us write now, substitute the value. IT will become plus 4. A1 is minus, so minus 0.065 e to the power minus 11.97 t, and A2 is positive, so plus 0.065 e to the power minus 0.53 t. So this will be the equation for current. So we can also again plot the equation quickly in MATLAB and see how this variation is coming. So let us do that quickly. I will just switch to MATLAB window. So now in this case, instead of voltage, we have current. So we'll comment this line and write the equation for current. So I is now current. So I is equal to 4 minus 0.065 multiplied by the exponential exp minus 11.97 multiplied by time and plus 0.065 multiplied by the exponential exp, and we have minus 0.53 into time t. So I hope this is correct. Minus 11.97 and minus 0.53, and the coefficients are 0.065 positive and negative 0.065, and the first case is plus. So let us plot it. So this is the plot we are getting. So anyways, there is a power cut, but we have already plotted the curve. So initially at time 0 we are getting 4 amperes current, and finally the current will decay to finally to 4 amperes. So this will be the curve. So initially it was 4 ampere, and so as we can see, initially it was 4 ampere at time 0. So this was 4 amperes at t equals to 0. That is what we are getting. At t equals to 0 it is 4 amperes. There is a sharp jump here, and finally in the forced condition the current will be 4 amperes, since the circuit here, as we have already seen, the inductor will behave as a short circuit, and therefore all the current will pass through this. So this suggests that we are getting a correct waveform for the current. So here I will end the class. We have already seen the circuits for parallel and series connection. We have already plotted the waveforms, and the conditions are matching. Okay, thank you for now. We'll meet in the next class. Thank you all.